Hello, everybody. Oh, you say hello. I should say yes. Good afternoon, everybody. Good afternoon. Great, yeah. So I should greet you properly. I've just learnt this after nearly 3 weeks, to greet you properly. Thanks, Emil. That's wonderful. The assignment, the last assignment, is going to be analysing some of Emil's data, which we'll talk about a bit later. But part of that could be using some of this regression framework, if you want. And so I'd just like to go through this again briefly. This is from yesterday's lecture, but I've changed the slides a bit to put more information in. So the crucial thing here is, although I talk about a treatment, because in this case I was talking about a trial of a new intervention. This could be anything. So this could be, in Emil's example, we might be looking at whether gender, whether you're male or female, affects your tendency to have TB. But we may want to look at the effect of many variables all at the same time. So in Emil's example, we might have gender in here, and then here we might have all sorts of measurements of a person's genes, what their ancestry is. And what we want to look at then is perhaps the coefficients of these genes, of these measurements. So we put in this multiple regression. Okay, so, and the syntax here is that we use LM, which means linear model. We do what we want to predict or explain, and then we do plus for the different variables. So in this example, when we put in, we know that the hand, they are bigger for males than females. Actually, I ran this again, and yesterday I didn't put the right numbers in here, because I think we get a more interesting result. Here, I want to see whether, if we allow for someone's height, there is still a difference between male and female hands. So we put both gender and height in to try to explain hand span. And when we do that, we get these coefficients. And when we get the confidence interval for the gender, we now see that the confidence interval does not include 0. Oh, so it does include 0. It does include 0. And so we can know the confidence interval for the effect of the hand. The best estimate is 1.16, and it goes from 2.34 down to minus 0.03. So our estimate for the mean difference between hand of a male and female of the same height, this is the difference for male minus female of the same height with the same x value, of the same height, is the crucial thing. And then we find that it's not significantly different from 0. So in fact, maybe men and women do not have any difference in their hands. It's just because men are taller. The data, we might want to check that. If we had more data, maybe that would not be the case. But with the data we've got, that could be the case, which I think we have an important scientific discovery. Well, okay, so just if you do summary, when you do one of these fitted ones, you get all this information. And I've just explained some of it here because if you use this technique, you might want to look at this to look at the interpretation. I don't think we have to worry too much about that. That's the residual distribution. But this is important. These are the estimates of the coefficients, these things, the numbers in front of the variables. And then the standard error, the t-value, which is just the estimate divided by the standard error, and the p-value, which is a two-sided p-value. Oh, that should have said less than 0.0, no, greater than 0.05. So you see for gender, our p-value is greater than 0.05. And that also, of course, fits with the 95% confidence interval, including 0. The same conclusion. Height is related. P less than 0.05, so height is related to hand width. We know that. But gender, if you allow for height, is not. And then there's lots of other stuff that I don't think we have to bother with too much. This is an estimate of sigma, 1.737. That's the estimate of the standard deviation of the results. But we don't have to bother with the rest of the thing. Okay, so this is the crucial thing to look at in the summary. Okay. Yeah, we don't have to bother with those. Is that all right? Is there any questions on that? You may have some questions when you try to do it. Yeah, any questions on that? All right, I'm sure you will have questions when you come to it. Right, okay, let's have a look at today's lecture, which is, I'm not going to talk for too long today, I don't think. But I wanted to show you some ridiculous statistics. This was in the newspaper, the English newspaper a few days ago, how the eggs factor reveals your personality. Outgoing people like poached eggs, while frying fans are hot stuff in bed. This is the worst bit of science I've ever seen. Scientists research the psychology of consumer choice. How do you like your eggs cooked reveals personality traits about secrets, about social class, and even sex drive. How you like yours. No, I know, it's just dreadful, isn't it? This was it. I found this because it was in the Cape Times as well. The Cape Times had this story. So here we are. Poached, scrambled, boiled or fried. We all have our preference for how to cook an egg. But the choice reveals more than our culinary tastes. It also highlights our personalities and reveals secrets about social class and even sex drive. Now look, what the scientists quizzed 1,010 adults. It's always 1,000. You ask 1,000 people. And that's because if it's a good survey, 1,000 is enough to estimate everything to within 3%. So if it's a good survey, you do ask 1,000 people. But then they did something which they don't tell us, that found that poached egg eaters are outgoing, boiled egg lovers are disorganized. Okay, well, I should have asked you first. Oh no! I should have first asked who likes fried eggs and who likes boiled eggs and who likes scrambled eggs. Oh, I wasted a good joke. Oh no, what a terrible waste. Okay, yeah, you can now say fried egg fans have a high sex drive. So who likes fried eggs? Yeah. Scrambled eggs aficionados are guarded, and omelette eaters are self-disciplined. So I hope you all like omelettes. Yeah. This was a study. You can guess what's going to come. This was a study for the British Egg Industry Council. It's not a bit of science. It's a bit of marketing. They're trying to sell eggs. They're trying to get this stupid story in the newspaper. It found that the average poached egg eater is likely to be happier than most. I mean, they must have done some statistics, and it must have been terrible. I'm trying to find the report. Here we are. You know, fried egg fans are usually from the skilled working class, and scrambled eggs are favoured by those without children. I mean, it's just dreadful science. But somebody did some statistics for this. I bet these weren't significant results. Okay, so that was just an example of bad statistics and bad science and how it happens. Okay, now I want to give some help to people because I know that there's a real problem with interpreting p-values. And sometimes I ask to explain the conclusions, or what do you conclude? So how do you put this into words? And this is a real problem. So I'm just going to suggest some words that people might use, some phrases, because the logic is quite difficult. Now, I've said that if p is less than 0.05, the usual thing, we would say there's evidence against the null hypothesis. Or we could say the evidence that the difference is real, that there is a true difference in height or response or something like that. There really is a difference. There's evidence for it. So, and if p is less than 0.01, people quite often say strong evidence. And if p is less than 0.001, they might say very strong evidence. So that's the kind of language that people would say. Evidence either against the null hypothesis, although, I mean, you wouldn't use that language in a newspaper article, but you might say evidence that there's a real difference. Now, the first thing is that the p-value is not the probability of the null hypothesis being true. So if I get, p less than, if I compare, height, of men and women, and I find p less than 0.01, that does not mean the probability that men and women have the same height, average height, which is the null hypothesis, equals 1%. It was less than 1%. This is the probability that H0 is true. And that is not the p-value. We don't even talk about this. We never mention that at all, the probability that the null hypothesis is true. If it's small, it's evidence that the heights are different. The average height is different, or strong evidence that the average height is different. It is not the probability that that they've got the same average height is less than 1%. So if p is less than 0.05, you can't say there's less than a 5% chance that H0 is true. Here I said 1%. Although that's the interpretation that everyone did for the Higgs boson. They got it wrong most of the time. Now, if p is greater than 0.05, in other words, a non-significant result, you can just say there's no good evidence against H0, or there's no good evidence for the difference. You can't say that, therefore, there's no difference. So, p greater than 0.05 does not mean there's no difference. It means there's no evidence for a difference. Now, it's a difficult logical thing that it means that, but it doesn't mean that. You see that? It's very confusing, very difficult. There's no evidence for a difference, but that doesn't mean that there's no difference. It just means we don't know. We're not sure. But we definitely, maybe there is, maybe there isn't, but we can't conclude that there is a difference. Okay, so there you have a look at those. This is very difficult. If there's some very nice websites that try to explain this, they often get it wrong, unfortunately. Most of the sites that explain it get it wrong at some point. It's a really tricky issue. Okay, so finally, remember, if a 95% confidence interval does not contain the null hypothesis, this is the same as p less than 0.05. Okay, are there any questions to this incredibly confusing work? Right, we're just, yeah.
Instead of 95%, if we use 99%, we compare p to
less than 0.01. Yeah. You just always take the inverse of these. It's always if it's 99.9, that would be p less than 0.001. So there's always the difference between them. So they should always correspond. Right. Okay. Well, that's to refer to. Yeah. Oh, just to say the Higgs boson, in the 4th of July when that was announced, on the BBC website, they described it They said this was they claimed that combining the two data sets, they had attained a confidence level at the 5 sigma point, about a 1 in 3.5 million chance that the signal they see would appear if there were no Higgs particle. So they've tried to explain a p-value on the website to the general public. So what does that mean? Just see if you can. Does that sound a reasonable explanation? We've got a normal distribution, and that's 1 standard deviation, and that's 2 standard errors, 3, 4, 5. And if we observe something here, it's about p less than, we know that this area above 2 is roughly 0.025. There's about 2.5% there. So if we do, this language says, if we observe something at 2 sigma, the p-value is about 0.025. 3, 4, 5. Now they observe something out here. This is H0, no Higgs boson. They observed a really extreme result. And if we, what's the tail area here? Well, we do P norm in R of -5. It's actually, I'm doing the tail area down here. This is -5. I want that area, which is the same as that area. And if I go 1 over P norm -5, I get 3.5 million. So that's what they did. They found something that was 5. In other words, their sort of T statistic, their test statistic, was more than 5. And so they calculated a tail area and found it was 1 over 3.5 million. And that's what they report. So that shows, even the big physicists discovering Higgs boson use p-values. The other thing is that it's one-sided. They just look at the high values. They're not doubling it. They're not doubling the p-value. Do you think that's comprehensible? Do you think that there's a way of describing a p-value? It's the probability of getting that signal if there were really no Higgs particle. So it's the probability of the data given H0 is what they're doing. Make sense? Yeah? Yeah, okay. It's not a bad attempt at getting it right. All right, okay. Let's do multiple tests. One of the things about the Higgs boson is that they searched everywhere for it. They did lots of hypothesis tests. And there's a real problem with multiple testing. If you do k independent hypothesis tests, then even if the null hypothesis is true, what's the probability you will get a significant result? So we're going to do it in a minute. We're going to do one in the class. But what I'm saying is if we do, if I'm testing, a null hypothesis. No, there's some chalk. If I'm testing H0 and I do, I do one test with some data, with data, X1, and then I do another one with data X2, another one with data X3, and I keep on doing lots of tests with new data. The probability of a significant result given H0 is 0.05 if I use a p-value of 0.05. If this is significant, meaning p less than 0.05. And similarly for this is 0.05. And that is 0.05. So it's like each time the probability of getting a significant result is about 1 in 20. And I'm trying lots of times. So I keep on trying to do this. And what this shows is that eventually I will get a significant result. Now, that's the idea. Let's try it. We'll come back to that in a moment. Yeah, okay. Can you get out a piece of paper and a pencil? I want a piece of paper. So we're going to do a lot of hypothesis tests. And, okay, now, we're going to test the hypothesis. Well, what I'm going to do is let's see if any of you are psychic. Can you read my mind? Can anyone there read my mind? Does anyone have magical powers here? I'm sure, yes, Adrian's got magical powers. Right, we're going to test his magical powers. I want you to read my mind. So, which of you is psychic? So the null hypothesis, so H0 is that nobody is psychic. So let's test that. Okay, let's test that. Now what I want you to do is I'm going to flip a coin, and there's two sides to this coin. There's one with an animal on it, and one with a sort of badge on it, the whole 5-rand piece. So let's say heads is the animal. There's no head, but we'll do, and tails is the badge, or whatever it is. Don't know what symbol or something. Okay, so what I'm going to do, I don't know what is it? Anyway, what I'm going to do is flip the coin. Then I'm going to look at it, and you're going to read my mind. Your magical powers. And write down what you think it is, whether it's a head or a tail. And then I'm going to, let's do a test. This one doesn't count. So, and then I'm going to say what it is. And if you got it right, just put a little ring around it. We'll do it 20 times. 20 tests. So essentially you just ring it if you got it right, and don't ring it if you got it wrong. And then at the end of it, at 20 times, you can tell me how many you got right. And Adrian's going to get them all right, because he's either a cheat or he has magical powers. Okay. All right, are you ready? Okay, you go already, right. So let's flip it. I'm going to look at it, and you're going to read my mind. What do you think it is? No. Oh, yeah. No. Okay. What do you think? Have you written down something? Yeah, right. An answer. And the answer is, it is a tail. Right. Okay. No cheating. Right. Okay. Next, number 2. Read my mind. And the answer is a tail. No, it's true. I'm not going to cheat either. So let's just write these down. Make sure people. So that was we've had 2 tails. Tail. Right. Okay. Next, number 3. Read my mind. And the answer is. Oh, I wasn't looking at it. Now read my mind. And the answer is a head. Right. Number 4. Right. Read my mind. Oh no, hang on. Number 4. The answer is it's a head. Right. Okay. Number 4. Right. Number 5. No cheating. Number 5. And the answer is it's another head. 3 in a row. Okay. Let's see if we can do 4 in a row. Number 6, and the answer is it's another head. So I'll do these in 5s. Okay, head. Oh no, I'll do it 20 in a row. 6. Right. Then again, and the answer is it's another head. Whoa! Look at that. 5 in a row. They do happen. And the answer is it's a tail. Okay. So we're up to 8. It's good, going well. Okay, let's flip it again. That's a good flip. And the answer is come on, read my mind, it's a tail. 9. Right then, come on. And read my mind. It's a head. Right, halfway through. Hope you're doing okay. All right then. Now, in oh dear. Where's it gone? Now, in number 11. Read my mind. And the answer is a head. Read my mind. Another one. It's a tail. 12, 13. Come on. I hope you got them all right, Adrian. It's a head. What are we doing? So far, so good. 13. Hope has anyone got them all right so far? No, right, and the answer is, it's a head. 14, 15. The answer is it's a tail. 16. Tail. 16 tail. Okay, 4 more. Oops. And the answer is a head. And next, read my mind. Tail. Now, soon we'll be able to see if anyone's psychic. Right. Head. And the final one, after that run of 5, final one is it's a head. Now, count up how many you've got out of 20. Let's see how we're doing. Okay. How many got none at all? I mean, that would be remarkable. That would be really spooky. How many only got 1? No. 2? No. How many got 3? How many got 4? Anyone got only 5? Did anyone only get 6 right? 7 right? Well, how many? Sorry, okay, what? 6. Anyone get 6 right? No. Okay, 7. Who got 7 right? I'm going to count. Hands up, right up. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Got 7. How many got 8 right? Hands right up. That's 4. 1, 2, 3, 4. How many got 9 right? 1, 2, 3, 4, 5. Okay. How many got 10 right? Yeah, that should be most common. Hands right up. We got 1, 2, 3, 4, 5, 6, 7. Did you get, sorry, no, 7. Okay, great. That should be probably the biggest one. How many got 11 right? Whoa. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wow. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 11. How many got 12 right? Aha, now we're getting clever. 1, 2, 3, 4, 5, 6 got 12 right. How many got 13 right? Wow, brilliant. 1, 2, 3, 4, 5, 6, 7. Wow, you're getting interesting now. How many got 14 right? Wow, Richard. 1, 2, 3 got 14 right. And did anyone get 15 right? Hey! You got 15 right. Cool. Did you realize that you had magical powers? No. So that's what we should have. Oh, 16. Anyone get 16? 17, 18, 19, 20. No, 16, 15 was the highest. Okay, now 15. What's the chance? Each of these is a test of a hypothesis of a thing. Now, in fact, the null distribution, what should the distribution of this be if it was just chance?
Normal.
Sorry? Roughly a normal, but what is it exactly? It should be binomial. It should be, it will look roughly normal. I mean, it does. It's a nice normal curve. But it should be a binomial with n equals what? 20 and p equals 0.5. Yeah. So if you look in, okay, so if I go into a binomial with n equals 20 and p equals 0.5, yes, brilliant. I find the probability, a one-sided p-value, of getting 14 or more. So these three people had p less than 0.06. Well, not good enough, not quite good enough. But 15 is p less than 0.05. A significant result. So we could say that you got a significant, this is a significant test that this is evidence for your psychic abilities. Now, do you think you do have psychic abilities? No, I don't. Actually, I don't think you do either. Now, the point is that this looks exactly like a binomial distribution. There's no evidence that any of you can do any, if you've got any skill about guessing this thing at all. But because we did 50 of these, nearly 50 of these, just by chance one of them is going to be in the tail. You're not going to all get 10 and 11. You will be out there. So I was pretty sure that at least one of you would get 15. I don't know who's going to be, but you can be pretty confident that at least one of you is going to get 15. So what would be really bad now if I wrote a scientific paper saying, about your psychic powers, in other words, only told anybody about you and ignored everybody else. That would be really bad. But it's what people do. They just pick the result, which is significant. So what we've done, okay, what about the maths of this? How did I think, doing 50, why was I pretty sure that we would find p less than 0.05? The point is, that this result, is actually the exact p-value is 0.021, but let's just say it was a 5% chance of that. The probability of getting this significant result, if none of you are psychic, is 0.05. But I've done 50 tests. So the probability, remember right when we did probability 2 weeks ago, when we want the probability of getting at least one, we do 1 minus the probability that none of them will be significant. Remember that? I wanted the probability that at least one person would get 15. So I do 1 minus the probability that nobody will get 15. And those are all independent. So I can just multiply these probabilities up. 0.95 to the 50 times. If I multiply 0.95 50 times together, take it away from 1, 0.92. So it was almost certain that I would get a result with p less than 0.05 out of 50 people. Do you see how that works? Because there's only a 1 in 20 chance that any of you will get an extreme result. But because there's lots of you, there's a really good chance that at least one of you will get an extreme result, which we've shown. So that's what's to do with, this is what's called multiple testing, the real danger of multiple testing. Here we are, here's the maths. If you do k independent hypothesis tests, then even if the null hypothesis is true, none of you are psychic. The probability that at least one have a p-value less than 0.05 is 1 minus probability they'll all have a p-value, no, greater than 0.05. Sorry, that's the wrong way round. Yeah, which is 1 minus 0.95 to the k. So if there's 20 people, you do 20 hypothesis tests, there's a 64% chance of wrongly rejecting H0 in at least one of the tests. So, in this particular case, this was 0.02. So I could say the probability that at least one person gets 15 or more right equals 1 minus the probability that everyone gets less than 15 right, which is 1 minus 0.98 times 0.98 50 times, which is something or other. I don't know. It's probably, I don't know, I'm guessing it's about 60.6 or something like that. Anyone got a calculator? Can anyone do that quickly? 0.98 to the power 50. Actually, I could do it on my phone, I think. So that I knew, if I can do this right, 0.98 to the power 50 equals 36. Yeah, it's 36. This is, yeah, oh, that's not bad. It's 0.63. So if there's 50 of you, there was a 63% chance that at least one of you would get 15 right. So it's not at all surprising. And, it was, maybe you wouldn't, but there was more than evens chance that someone would get 15 right, and they did, which is just right. So, is that okay? Does that make sense? Any questions on that? It's a really important thing because it shows the dangers of doing lots of tests, and I've got a joke cartoon about that in a minute. Okay, so what do people do about multiple? Oh, here's the joke. Okay, here's the joke. This is one from the web. They say jelly beans cause acne. Jelly beans are the sweets, and acne is your skin problems. Okay. Scientists investigate, and they said, well, we're playing Minecraft. We found no link between jelly beans and acne, p greater than 0.05. Okay, that's what the scientists say. That settles that. And somebody then says, I hear it's only a certain colour that causes it. So he calls the scientists, and they test every colour. We found no link between purple jelly beans and acne. We found no link, p greater than 0.05. We found no link between brown jelly beans and acne, p greater than 0.05. We found no link between pink jelly beans, between blue jelly beans, green jelly beans, salmon jelly beans, red jelly beans, turquoise jelly beans, magenta yellow beans, yellow. Oh, here we go. We found no link between grey jelly beans, tan jelly beans, cyan jelly beans. We found a link between green jelly beans and acne, p less than 0.05. So they tested and tested, tried every colour, and then they found one with a link. And then nothing between mauve jelly beans and beige jelly beans and lilac jelly beans and black jelly beans and peach and orange jelly beans. So they did 20 tests. You see, they've done 20 tests, and one of them has come up with a result. And so that's what gets published. Green jelly beans linked to acne. With 95% confidence, only 5% chance of coincidence. Now, it's a cartoon. This really happens, though. That people test lots of things and then only report the one where they get p less than 0.05. So this is how some science works. And it is a really dangerous thing. It's called it's sometimes called a fishing expedition. A fishing expedition is when you keep on looking at the data and testing everything and comparing everything until you find something with p less than 0.05, and then you publish it and tell everyone about it. And it's really bad practice, but people do it. Okay, how could we get around that? There are various tricks that people do. You can adjust the p-values for multiple testing. So the simplest thing people do is called the Bonferroni inequality. And that's because if I do k tests with a small, looking for a small p-value, then the probability of at least one significant equals 1 minus p to the k. That's what we did before. That's what we did there. Oopsie. Yeah. 1 minus p to the k. But that's roughly 1 minus p to the k is very roughly 1 minus pk. Just taking the first term of the expansion, which is roughly p times k, which is the p-value times the number of tests. And so that's, you might think, is the appropriate p-value. If you do k tests and you find one with p equals 0.01, you multiply that by the number of tests you did to give the sort of honest p-value, to allow for the fact that you looked at all these tests, or you did all these tests. So that's called the Bonferroni one. You just multiply. If you do 10 tests, you find one with p less than 0.01 or 0.1, you report p equals 0.1. You multiply that by 10. So in our thing, we found p equals 0.02 as our most extreme. We'd multiply by 50, and we'd end up with 1, and that would say it wasn't interesting at all. Another thing people do is use wider confidence intervals. They use 99% rather than 95% if they're doing lots of tests. Another thing people do is demand a very, very low p-value, like 0.00001. And that's what the Higgs boson team did. They demanded a p-value less than 1 in a million. That's it. That was the Higgs boson p-value they wanted. Because they had 1 in 3 million, in fact. But they wanted less than 1 in a million. Another thing people do is demand replication. Again, the Higgs boson team did that. The multiple teams got the same results. And another thing, which we won't go into, but is of increasing importance, is to control the false discovery rate. And people who start, when you're working in bioinformatics or functional MRI, magnetic resonance imaging, you're doing thousands of hypothesis tests. What Paul will be talking about later, when you're doing brain mapping, and you've got the brain, and you're looking for little areas of the brain which light up, you're doing thousands of hypothesis tests. And in brain mapping, they often want p-values like that. Similarly, in genetics, you're testing for thousands of genes. They demand tiny p-values because they're doing so many tests. So that's these are some of the strategies that people use. Okay, and that's the end of that. Are there any questions on that stuff? Okay, right. Well, what I'm going to do now is we're going to go upstairs. There's two things I want to mention. First of all, the practical that we had, I've changed it a bit just to make it a bit clearer. There are some bits that weren't clear. So I hope this is a bit clearer what you need to do. But it's the same questions as the previous practical. And I would like you to go through this because it's quite important and it's a good test. Now, the other important thing, which if you do the practical you can start on, is the final assignment, which is analysing some of Emil's data. This is a stats assignment 2, and basically it's reading in the data, doing plots, doing comparisons, but we're not giving you any code. You'll have to adapt the previous things you've done to put them together. And I think we just asked a whole lot of questions. And we're asking you to produce a short report with graphs summarizing your conclusions. Mm-hmm. So, so that's all. And so, in a way, everything we've done, you can use in that. There's all sorts of, a lot of ideas there, but basically you have to look at that data and try looking at it and see what is in there. Maybe I haven't done that. Maybe there's nothing in there at all. But you'll have to say whether there's something in there. Okay, so if we go upstairs now, it'd be good if you finished off the previous practical and then the stats assignment. And we'll also then have some time to look at this tomorrow. And when, we'll tell you when we might want this. Okay, is that all right? Okay, great. Thank you very much.